Okay, so on this problem here, we've got this weird yo-yo, I guess, that's two spheres connected by a spindle. Spindle basically is like a uniform cylinder spinning on this axis through its middle. And so we just did two things here. First, we need to figure out the rotational inertia, the I value for this whole collective system. So it's not just a given thing. We're going to have to add them all up. And then what we're going to have to do is figure out the torque on this that causes it to spin based on how much moment of inertia there is to figure out how fast it accelerates. All right, so the first part is pretty easy, actually. Just take two spheres, find the moment of inertia, and add it to the uniform cylinder here. So that's what I'm doing here. Okay. So the I value of the sphere is 2/5 mr squared. M1 is and R1 are the mass and radii of the spheres. Double that plus this acts as a uniform cylinder, which is 1/2 mr squared. M2R2 is the mass and radius of this spindle, the cylinder around which this yo-yo spins. All right. So plug in all this number from the problem, find the I total, which is this value here. It's kind of small. All right. Next, we need to do a force analysis here. Now, mg, I should have actually drawn it here because mg actually acts at the center of mass of the system, so it creates no torque. It looks like it's going to do torque, so they count me off on the AP for this. So I do my force vector here through the center of mass, but tension is acting not at the center of mass and therefore does create torque. So if down is positive, the net force on the whole thing will be the weight of the whole thing minus tension, mg down minus tension up. And so if I solve that, this is set that equal to MA for the whole system, equals the weight of the whole system minus T. T equals this expression right here. Okay. So then finally we want to find how fast this actually accelerates down. So this is going to have a certain acceleration just linearly down. So to do that, we set torque equal to torque. So torque is both force times lever arm, and it's also I alpha. That's what I'm doing here. The torque is only being generated by the tension in the string. Remember, mg doesn't create any torque, times the lever arm of that. So that's this T times that R. So you got to make sure you put in the right values over here. And then that equals I alpha. We've already figured out the I of the whole system, so we plug that in there. And we substitute in for alpha, we put in tangential acceleration over R2. That needs to be the radius of the spindle, not the spheres. And I can substitute that in here. It shows up there, and so now I know everything here. Oops, I lost my R here. I forgot to draw that in here. R2 should be times this quantity. I left that out. So add that R back in times this value, and then you're just solving now. The only thing we don't know is the linear acceleration, and so it comes out to that.